Good afternoon, everyone. We are ready for the next presentation by Joakim Kennedy on a deep dive into Go malware using metadata to empower the analysts. Joakim, all yours.
Good afternoon. So the graveyard slot, so let's get through this. So a little bit about me before I start. So my name is Joakim Kennedy. I'm a senior principal security researcher for Anomaly, and we're focusing on researching and gathering threat intelligence that we are providing to our customers. So the agenda for this talk is, first we're going to go over and do a little bit of an introduction to Go, the programming language. So most of us here in the room will have sort of the same background knowledge. And then we're going to look at how we can recover function information from stripped binaries that have been compiled by the Go compiler. And then we'll take a look at some malware, and we'll apply sort of this with a tool and extract and get information from them that otherwise is sort of hidden. And then we'll take a look and see what else we can find in the binaries and what we can draw from those conclusions. So to start with, Go was sort of worked on internally at Google in the start of 2007 by Robert Griesemer and Rob Pike and Ken Thompson. It's designed to be a memory-safe language. It's using a garbage collector, and it's static typing. The language was sort of designed to be a new language for the 21st century, so it has well support for multi-threading, networking, etc. The language is relatively simple and easy to read, which is mainly sort of from design. So this is the hello world in Go. All code in Go is part of a package, and the package that's been executed is called main. And so in here we're sort of looking for the main package with a main function that would execute. We're importing a standard library for doing some formatting and printing, and essentially just writes hello world to the output. Go has support for sort of most standard numerical types. We both have for unsigned and signed integers of specific size. It also has support for floats and complex numbers. It also it has a couple of aliases. So for example, a byte is an unint 8, and then a rune, which is more used for characters. So Go has support for UTF-8, and this is sort of handled by rune as a UTF-8 character. It also allows sort of the programmer to use a non-size sort of integer. So you have an unsized uint and an int. The sizes of them are dependent on the architecture that you're compiling it to. And then it also has a pointer representation for these. Strings. So Go has first-class support for strings. You can either sort of define it as a top, where you tell it that this is a specific string, or you can allow the compiler to do resolve the type for it. Under the hood, a string is different. Go strings are different from C strings. So it's using two words to represent the data. You have first a pointer that points to where the data is located, and then a length parameter. And so this makes length calculations of strings constant. Arrays, and then on top of that, Go has a sort of a functionality called slices. Arrays are the same as what they are in C, where slices are more similar to Python lists. So a slice can grow, and it's an abstraction on top of arrays. The slice is represented by first a pointer to where the data start, then the length of the current slice, and then a capacity. The capacity, if it's set to 0, the slice can grow until you run out of memory. If you have a value, that's how far it can grow, essentially. Structs are very, very similar to how it's in C. It's just laid out in memory. And the way object-oriented programming is done is through interfaces where you sort of specify a function signature, and as long as the type implements that function signature, it sort of satisfies the interface. And under the hood, this is done through a vtable that will point to the specific functions, and then a pointer to the actual underlying struct. So let's take a look a little bit under the hood, what happens when you compile it. So this is a snippet from a malware. This is one of the first bits that runs. So what it does is it first takes and reads in the argument list that was executed. So what it's looking at for is the first entry in the argument list, which will be the name of the binary that was executed. It will read this one move it into REX, and then take the next parameter after, which would suggest that this is a string. It then will move this onto the stack. So here you have the pointer to where the data starts, and then your length parameter, and then it will call a standard library just to get the base element. And the return value is actually returned also on the stack. So you see the calling function then basically pulling those data off the stack and put it into its local variables. So the difference we have, normally you would see just a bunch of push and pops. The Go compiler instead is opting for a faster runtime over smaller size in terms of the binary. Sort of on top of this, since it's designed for multi-threading and multi-concurrency, it has a concept of a Go routine. A Go routine is similar to a thin thread. It's executed via this keyword, so you actually will call Go before the function that's executed. And then this is then put on a scheduler that runs internally in the runtime. And the runtime selects between the different Go routine who will be executing what. So it's basically scheduling within the actual current application. And under the hood, this is done through the call to new proc, which takes a size of integer and then a function pointer. The size tells the scheduler how many arguments this function takes, and it requires that all the arguments for the function to be called has been pushed on the stack before it's executed. So essentially you will have this structure that's kicked off. Okay, so now we kind of know a little bit how the what's under the hood. So let's take a look at how we can actually recover functions information. So here we have the simple demo program. So what essentially we're going to do is just panic, which is the way Google Go throws exceptions. We're just going to panic hello world. And if we compile that and tell the compiler to strip the binary and remove all the debug information, and output from file tells us that this is a stripped binary. And then when we run it, we get the exception which says this file path where actually the exception happened. So it tells us that we throw an exception on line 4. So even though we've removed all symbols or external symbols, Go still have a capability to figure out which source line, actually this exception was thrown. So where this comes from, if you take a look, you can actually find the strings for these function names, and they're located in a table that's called Go PCLN tab, which is for alpha binaries, it's separate section. This table is a sort of a heritage from, or something that came in from Plan 9. So this is a man output from man out and on Plan 9, and it's talking about that you have a PC line number table in the binary. Further down in the man page, it says that this is used to recover source line number from a failure. So this functionality was added to the Go compiler in version 1.2, and it is there to sort of provide a accurate and a way of debugging and figure out where the exception was thrown. And luckily for us, who wants to sort of utilize this to extract information from stripped binaries, the debug package in the standard library has functions to read this table and extract it. This is a snippet of code that's taken from the test, which would read in this on an ELF binary. It looks like it's expecting the symbol table, but luckily the symbol can be empty, and it will generate the table correctly. So the table that's returned has, in most cases, an array of internal like functs, and then it has this line table. Using the line table, we can actually get from a program counter, get the source code line number, or vice versa. We can use the source code line number to find the program counter in the binary. So this is kind of very, very interesting and useful when we want to look at malware. So let's take a look at some. So I just have a little tool here that is sort of reading this table. It will extract all the functions in and just look at the specific one for the main, and then packages that are not imports or third-party vendors or sort of standard library, and just focus on the malware code. And it will try to guess. Not right. No, I can't. I'll have to start over then. So, it will hopefully get more text out. So it's using the information and tries to guess the length of the functions in the source code, and then also sort of structure a source code tree. So here's an example for this is a malware that was reported about a year ago by Cisco Talis. And they sort of reported it being something that was scanning and looking for SSH servers, and then brute forcing them and sort of spreading that way. And what we have essentially is it's finding where the package of the main. So this is the source. Look, this is actually a folder location where the file was located when it was compiled by the author. Here's the source code file. And then under there you have sort of all the functions, starting from the first line number, starting actually from line 188 or 181. And then it's sort of guessing. So I'm guessing there's a bunch of structs defined on top of that we can't see. So that's from this one was only targeting mainly like Linux malware. At the end of last year, there was a new version or one version of Robert that was found. I think it was starting in October. This is a malware that's used by the Russian APT group, APT28, and it's a downloader. They have a way of writing it in multiple languages to sort of throw off Analyst. And one of the samples you could get was representing sort of all of the functions that we have. So they hadn't done any obfuscations. So there've been a couple of sort of malware that's been obfuscated. So for example, we have one way Analyst gets through this, or malware authors, it's sort of by renaming the functions. So we can't sort of tell from the function name of what it's doing. We do have still the package name, but then also all of the different libraries that they're using are not obfuscated. So it's a little bit of a hurdle, but still we're working on it. So just on top of sort of function names, it's also possible of recovering type information. So this is a simple little demo. And in this sort of code, we're defining our own struct that just will contain one string and one integer. And then our code just instantiates a new version, like a new instance of this, and assign a string and an integer to it, and then we will just print out what the struct is. The compilation of this will sort of return this kind of code, just sort of highlighting the important part. At the bottom, we see the call to printf. Here we see the format string being pushed to the, actually being loaded onto the stack. And then we can see the two different values added to the struct. And then before that, we see a call to new object. And it's called on this offset is used in the call. And if we, here's a sort of a hex dump of this offset. There's a clear structure. There's a bunch of structures afterwards. It looks pretty much the same. And what it turns out is this is a type that's called _type. And this is the first three lines from that hex dump sort of translated onto the struct. This actually would tell, so this is what's being used in that new this new object call. It's using this and passing that to malloc, so it knows how much memory it needs to allocate. But the structure contains other information that's very, very interesting from sort of a reverse engineer. One really cool feature is the kind section. So this is in enum, and if you look in the source code for the Go compiler, this is returned as a kind struct. So we know now that what's here is referred to as a struct. The other interesting part is this name off, which is an offset to a name type, which is a internally sort of reported, which is an internal structure. So it's its own type, and it's just a structure that holds a pointer to a byte. And using that, we can calculate where this name is located. In this sample, it's based on where this list starts, and the list starts at the section, so we can actually just take the section, absolute location, and then just add the offset, and we'll get where this is located. And it returns this byte, pointed to this byte, and the function, this type has some methods to return the string representation of it. And if you look at that one, it basically jumps three steps ahead, and that reads off the actual string, which is, if it's here where it's pointing, here's where the name starts. And we've basically gotten that the name of this item is called main.myStruct. So we have both the package name and what the author called the actual structure in the source code. And there is more stuff below it. So now when we know that it's a struct, we can actually look up and see what the real type is there. And this is the real type. So it's actually a underscore type that's been embedded in a bigger struct. And right after that, we should have a name type, which is, again, another struct, and then some struct fields. The struct field is sort of a little bit of an inverse of what the main struct is. So it will have a pointer to some names, and then their own types. So we can essentially just unwind this and reconstruct what type this is. So taking the other section, here is we basically just translating. So here's we have the location where the package name is, which in this term will be just main. We have the fields, which will be starting from here. As here's where the offset is for the data. And then we have 2 and 2, so we just know we have 2 fields in the struct. And then looking at this offset is actually just just points down right below it. And there, if we can actually just translate these values. So we know it's 2. We can get the name, and we can sort of get where we can figure out where the type is located. So if we just dereference those, we'll get the actual name of the fields within the structure. And so finally, we can sort of just reconstruct what this initial source code was. So sort of just to conclude, so Go binaries, initially when you look at them from as a reverse engineer, they're beasts. It's not uncommon to come across a binary with 6,000 plus subroutines. So starting out, if you don't have the right tooling, it's really, really hard. But if you have the right tooling, or you develop the right tooling, it's relatively easy to actually sort of deal with these. There's also a massive amount of metadata. And this is not the only thing that's there. The sort of interesting part is here, like we can actually recover the functions and the type information. And since this is directly coming from the source code sort of being translated, even if there's a slight changes to it, we can still sort of see similarity between other samples. You can also do it's interesting that you can do an educated guess of the source code structure. So there are a couple of samples that I've come across that have been compiled in different operating systems. But you still have sort of the same source code structure, so you can map across that they're the same. It also allows you to do sort of like metadata analysis, so you can look at samples that have been compiled for ARM or MIPS, and then map them and sort of compare them to other samples, and just using the source code analysis, you can sort of see that they're similar or the same. They're essentially coming from the same source. So with that, I can take any questions if there are any.
What kind of tools do you use to RE Go samples?
So this is its own sort of the tool that I use is a tool that's written in Go itself. It has the capability of be used in other tools. So far I haven't written an IDA plugin for it, but it works for R2. So if you use R2, it will basically run, instead of sort of printing out the structure, it will reconstruct the symbols and inject them like it was a non-strip binary. So.
Yeah, I think you partially answered my question. I was going to ask about IDA Pro support.
It's in the plans.
Hello. Does the runtime depend on that metadata? Could an attacker strip it out if they were dedicated?
The type data, I'm pretty sure it's used by the reflection capability. So if you did strip it out, you may end up crash in random places. And I think it's the same with the information that's used to recover the function information. While it is used for the panics step, I remember reading a while back where people were using just a normal strip tool to strip Go binaries, and it kind of resulted in random crashes because it was selectively basically removing stuff that it needed. To be honest, I don't know what happens if you remove that table. And now, since functions are sort of first-class citizen in Go, this type information should also there's another representation of the function in that type list. So if you walk the type list and get all of these different types, you can also find all the functions. And you should, in theory, be able to recover that.
Quick question about like, I'm right here. Here we are. So have you ever looked at a binary that has used the project Go obfuscate? And do you have any insights as to how that works, or does it provide obfuscation against some of the things that you've spoken about today?
So I haven't looked at that project, but I've come across a bunch of malware that are obfuscated, but they're only obfuscating their code. So all the dependency that's pulling in are not obfuscated, and the standard library are not obfuscated. So it is just a little bit of a hurdle. Now you just have a random string, but you can see all the calls that it's doing. So unless it would obfuscate all of the functions you have, which may get some problematic, so.
Okay, I think we're out of time. If you have any more questions, you can just talk to Joakim after the session.
Yep.
On behalf of BSides, we thank you for your presentation.
Thank you.
Thanks.